Okay, this is a bit ridiculous, but I am learning math one step at a time and figured, what the hell, why not stream it? All because we wanted to understand what was a vector. Um, let's see, polynomials appear in many areas of mathematics and science. For example, they are used to form polynomial equations, which encode a wide range of problems, from elementary word problems to complicated scientific problems. They are used to describe polynomial functions, which appear in setting ranges from basic chemistry and physics to economics and social science. And they are often used in calculus and numerical analysis to approximate further functions. In advanced mathematics, polynomials are used to construct polynomial rings and algebraic varieties, which are central concepts in algebra and and algebraic geometry. The word polynomial joins two diverse roots, poly meaning many and nomen or name is derived from the binomial by replacing the Latin word bi with the Greek poly. That is, it means a sum of many terms, monomials. The word polynomial is first used in the 17th century. Okay, so the part we got up here is that a polynomial is a mathematical expression, but it's consisting of indeterminates, also called variables. What I was piecing together is that it always seemed to be in the positive range. I mean, it wasn't including negative numbers. Polynomial ring. In mathematics, especially in the field of algebra, a polynomial ring or polynomial algebra is a ring formed from the set of polynomials in one or more indeterminates. There's a ring in this case. In mathematics, a ring is an algebraic structure consisting of a set with two binary operations called addition and multiplication, which obey the same basic laws as addition and multiplication of integers, except that multiplication in a ring does not need to be commutative. In mathematics, a binary operation is commutative, there we go, commutative, if changing the order of the operands does not change the result. It is a fundamental property of many binary operations, and many mathematical proofs depend on it. Okay, so like 3 plus 4 and 4 plus 3 is its example, or 7 times 3, 3 times 7. When you're dealing with two positive numbers, it doesn't matter which order goes first. When it's addition and multiplication. Okay. Okay, so which obey the same basic laws of addition and multiplication of integers. is an algebraic structure consisting of two sets of binary operations. So ring elements may be numbers such as integers or complex numbers, but they may also be non-numerical objects such as polynomials, square matrices, functions, and power series. What's a power series? In mathematics, a power series is one variable. In one variable, it's an infinite series of the form E. Well, it's not E, I guess it's just an infinite. We've got where n represents the coefficient. In mathematics, a coefficient is a multiplicative factor involved in some term of a polynomial. Oh, you know what? This is gonna make little to no difference, but let's pull out my avatar, because though it's subtle, oh, we don't want that. There we go. A little bit more interesting. Okay. The coefficient of the nth term. Well, we're going to learn what a coefficient is. In mathematics, a coefficient is a multiplicative factor involved in some term of a polynomial, a series, or any other type of expression. It may be a number without units. A number without units, in which case it is known as a numerical factor. It may be a constant with units of measurements, in which it is a constant multiplier. Without units is maybe with negatives. Dimensionless quantities, or quantities of dimension 1, are quantities implicitly defined by a manner that prevents their aggregation into units of measurement, typically expressed as ratios that align with another system. These quantities do not necessitate explicitly defined units. For example, alcohol by volume, ABV, represents a volumetric ratio. Its value remains independent of the specific units of volume used, such as milliliters per milliliter. It feels like a really stupid milliliters per milliliter. The number 1 is recognized as a dimensionless base quantity. Dimensionless base quantity. Radians serve as a dimensionless unit for angular measurements. Okay, so it's the term used that in of itself does not have a value. Its value is derived in relation to something else. So its value, like a radian, its value is how big the circle is. It's a radius. The radian, denoted by the symbol rad, is the unit of angle in the International System of Units, SI, System of Units, SI, and is the standard unit of any angular measure used in many areas of mathematics. Is defined such that 1 radian is the angle subtended at the center of a plane. Subtended. Look up subtended. Angle subtended by the arc. Wow, that is so dark. It's fine. Angle subtended by arc CD from point A. Angle subtended by arc CD from point B. An angle subtended from Latin. From Latin for stretched under by a line segment in an arbitrary vertex, is formed by 2 rays between the vertex and each endpoint of the segment. For example, a side of a triangle subtends the opposite angle. More generally, an angle subtended by an arc of a curve is the angle subtended by the corresponding chord of the arc. This is so complicated. Oh, it is honestly remarkable to me that the closer you get to defining the specifics of what is this thing, just dialing it down to its simplest form, it gets so complicated. It's that it becomes more and more complex the closer you get to pinpointing something exactly. Though I suppose that really is math in a nutshell. The closer you get to defining what something is in math, the more complex the illustration becomes. Because when you think about it contextually, what is a tree defined in math? And you have to understand all of the different ways in which a tree can be conveyed. understand how it can be conveyed in math. Okay. Subtended by the arc. More generally, an angle subtended by an arc of a curve is the angle subtended by the corresponding chord of the arc. For example, a circular arc subtends the central angle formed by the two radii through the arc endpoints. A circular arc is the arc of a circle between a pair of distinct points if the 2 points are not directly opposite each other. One of these arcs, the minor arc, subtends an angle at the center of the circle that is less than pi radians, and the other arc, the major arc, subtends the greater angle. Okay, so we're looking at basically it's the center line, but I was thinking of an acute angle, obtuse angle, and I'm not sure what it would be called if it exceeded over 180 degrees. A major arc. Minor arc, a major arc. A central angle is an angle whose apex or vertex is at the center O of a circle and whose legs or sides are radii intersecting the circle in two distinct points, A and B. Central angles are subtended by an arc between those 2 points and the arc length at the central angle of a radius 1. Let's finish reading that. A central angle is an angle whose apex or vertex is the center O of a circle whose legs, sides, are radii intersecting the circle in two distinct points, A and B, central angles, and subtended by an arc between those 2 points. And the arc length is the central angle of a circle of radius 1, measured in radians. The central angle is also known as the arc's angular distance. The central angle is known as the arc's angular distance. This right here which in other words is maybe the degrees. Arc's angular distance, so this is I don't know, what is that, 25, 22 degrees. The arc length spanned by a central angle on a sphere is called a spherical distance. The great circle distance, orthodromic distance, or spherical distance, is the distance between 2 points on a sphere measured along the great circle arc between them. This arc is the shortest path between the 2 points on the surface of the sphere. On the surface of the sphere. So it is always curved. The size of a central angle. Uppercase, lowercase, or ancient Greek. Let's see. Pronunciation. Theta. The pronunciation of the Greek letter theta is represented in the International Phonetic Alphabet. Friction as the voiceless dental fricative. Fricative. What a word, I like that. Which is the same sound as the th in the English word thin. This sound is produced by placing the tip of the tongue just behind the upper front teeth and forcing air through the narrow gap, creating friction. Okay, so theta is uppercase, lowercase, ancient Greek, theta, modern, theta is the 18th letter of the Greek alphabet. Okay. Theta in math. In mathematics, the Greek letter theta is primarily used as a variable to represent a measured angle. A variable to represent a measured angle, especially in trigonometry, geometry, and calculus. It is the 18th letter of the Greek alphabet and is commonly employed in trigonometric functions such as sin, or sine, cosine, and tangent, where it denotes the input angle. Sin, theta, cos, theta, tangent, theta. This symbol is fundamental in defining relationships within right-angled triangles, where theta represents one of the non-right angles in a polar coordinate, and in polar coordinates, where theta is the angular coordinate describing the direction from the origin. The angle theta can be measured in degrees or radians, and its value is crucial for solving problems involving circular motion, periodic phenomena, and coordinate transformations. Oh, that's old. Okay. Primarily used as a variable to represent a measured angle. The size of central theta is 0 degrees. Is that less than theta? Less than 360 degrees, or 0? Less than theta, less than 2 pi radians. When defining or drawing a central angle, in addition to specifying the points A and B, one must specify whether the angle being defined is the convex angle less than 180 degrees or the reflex angle greater than 180. Excuse me. Oh, so that's what it's called. Convex reflex. Equivalently, one must specify whether the movement from point A to point B is clockwise or counterclockwise. So this is saying it's a convex. The less than is for a circle. For theta is saying it is a convex angle. Less than, smaller. Okay. 0 degrees is the point. So 0 degrees theta difference to 360 degrees. So the size of a central angle. Center point of theta for a full circle, or 0 theta in 2 degrees. And this is saying any 2 radians, which I suppose this is also saying. Okay, I'm gonna sit on that for a second while I. That makes sense so far. central angle is the angle whose apex or vertex is the center theta of a circle. Or maybe it's just saying O for the placeholder in the image. Angle AOB is a central angle because it's an angle that involves the center of a circle. Okay. Central angle, center of circle angle. Here we go. More generally, an angle subtended by an arc of a curve is the angle subtended by the corresponding chord of the arc. For example, a circular angle subtends the central angle formed by the two radii through the arc endpoints. Okay. For example, the circular arc. Circular arc is the arc of a circle between a pair of distinct points if the 2 points are not directly opposite of each other. If the 2 points are not directly opposite of each other. A circular arc is the arc of a circle between a pair of distinct points. If the 2 points are not directly opposite each other, one of these arcs, the minor arc, subtends an angle at the center of the circle that is less than pi radians, 180 degrees. Okay, so it's an acute angle. And thanks. And the other arc, the major arc, subtends an angle greater than pi radians. Greater than pi radians. Radian is I think this is the pi radians is 180 degrees. Greater than 180 degrees. Because a radian is 2 points, 2 lines drawn. Pi radian is half of a circle. Okay, so pi radians is half of a circle. If you have 2 of them, you would have a diameter straight line. If it's greater than 2 pi radians, it would be this. So 2 pi radian is 180 because less than it's going to be in the 180, greater than it's going to be. Okay, that makes sense. It's basically a pi radian is measuring a diameter, and is it greater than or less than that? So major arc subtends an angle greater than pi radians. The arc of a circle is defined as the part or segment of the circumference. The arc of a circle is defined as the part or segment of the circumference of the circle, so measured on the outside. A straight line that connects the two ends. A straight line that connects the two ends of the arc is known as a chord of a circle. So the question is, are these the chord, or is the line from here to here a chord? Or is this the chord? A straight line that connects the two ends of the arc is known as a chord of a circle. So it's either this. This is a curved line, though. And it's a straight line. If the length of the arc is exactly half of the circle, it is known as a semicircular arc. Exactly half of the circle. Semicircular. Okay. Known as a chord. Let's read this one more time. A straight line that connects two ends of the arc. Two ends of the arc is known as a chord of a circle. A chord from the Latin chorda, meaning catgut or string, of a circle. Chorda means catgut. I do remember hearing that once upon a time they did make musical instruments from catgut. Yeah, glad we don't do that anymore. Wow. What kind of a thought process would go through somebody's mind to get them to consider catgut for a musical instrument? Ooh, okay. Straight line. But we're going to read a little bit just to make sure I'm understanding right. Okay. A chord. Latin chorda, meaning catgut or string, of a circle is a straight line segment whose endpoints both lie on a circular arc. If the chord were to be extended infinitely on both directions into a line, the object is a secant line. The perpendicular line passing through the chord's midpoint is called sagitta, Latin for arrow. Maybe sagitta if it's sagitta. We're gonna find out how to say this. Let's see if sagitta. Okay. The keystone of an arch. Oh. In geometry, the distance from a point in a curve to the chord, also the versed sine of an arc, so called from its resemblance to an arrow resting on the bow and string, the larger of two otoliths, or ear bones, found in most fishes. I really like this analogy, bowstring and arrow. This is the first sign of an arc, so called from its resemblance of an arrow resting on the bow and string. Okay. So it is a straight line through. Circular arc. For example, a circular arc subtends the central angle. Formed by two radii through the arc endpoints. So this has got a curve. Example of angles subtended by an arc from 2 points. What I'm seeing here is that this would be the central angle. Well, right over here, it would be a center dot. And it has the point there, point there. Why are they picking this specific point or not anywhere else in here for it to connect? Maybe it's because it's an equal distance from the center of this circle. Well, no, this would be a big circle. It'd be like over here. More generally, an angle subtended by an arc of a curve is the angle subtended by the corresponding chord. Okay. So this is the line corresponding chord of the arc. So how is it as it's extending off? It's finding this point by seeing how far this line reaches out past. So if the center is here, goes there. It's the secant and the tangent where they meet. Okay. Angle subtended. So these are the lines that are extending beyond. An angle subtended in Latin is stretched under by Latin for stretched under by a line segment at an arbitrary vertex is formed by two rays between the vertex and each endpoint of the segment. For example, a side of a triangle subtends the opposite angle. Okay, so that's what I'm understanding is it's drawing the lines that are outside of the circle that extend beyond it. That are its connecting points. Okay. Dimensionless quantities. Okay. So those lines outside of the circle would be a subtended line would be a dimensionless line because it's outside of the circle itself. So okay. Coefficient is a multiplicative factor involved in some term of polynomial series in which, or any type of expression, it is the number without units. That's how we got there, number without units. In which case it is the numerical factor. It may also be a constant with units of measurement, in which case it is a constant multiplier. A number without units. Interesting. The numbers outside of a circle in relation to the circle are numbers without units are I wonder if they would be considered negative numbers. Okay, where an represented the coefficient of the nth term. Coefficient was coefficient is a multiplicative factor involved in some term as a polynomial. I want to say coefficient just means answer. Coefficient definition. That which unites in action and something else to produce the same effect. Math, a number or letter put before a letter or quantity, known or unknown. A number or letter put before a letter or quantity, known or unknown, to show how many times the latter is to be taken. Okay, so it's 3x. The 3 is the coefficient. 6x, bx. Here 6 and b are coefficients of x. Physics, a number commonly used in computation as a factor. Oh, that's how we got to it. Factor, f. Factors, how many times? Expressing the amount of some change or effect under certain fixed conditions as to temperature, length, volume, etc. 3x is 3 times. It's f 3 times. Function 3. Okay. The coefficient of the nth represents the coefficient of the nth term. Oh, so 3 times. Do it 3 times to n. Always wondered what that meant. This is a function. A function times to n term, and c is a constant called the center of the series. Power series are useful in mathematical analysis where they arise as Taylor series of infinite. Taylor series, the Taylor series or Taylor expansion of a function is an infinite sum of terms that are expressed in terms of the function's derivatives at a single point. For most common functions, the function of a sum is its Taylor series are equal near this point. I didn't get it, but where they arise as Taylor series of infinitely differential functions. In fact, Borel's theorem implies that every power series is the Taylor series of some smooth function. Borel's lemma, named after Emil Borel, is an important result used in the theory of symptotic expansions of partial differential equations. Partial differential equations. Differential would be differing, partially different equations. The differential is slightly different here. Maybe it's just more exacting. It's saying different answered equations. Power series are useful in mathematics. Okay, where a n represents a coefficient of the nth term and c is a constant called the center of the series. Powerful series are useful in mathematical analysis where they arise as Taylor series. Of infinitely differential functions. So if I'm getting it right, it's saying we've got an equation on this side, an equation on this side, and where they overlap, where they are the same, that is the Taylor series. Because they're an infinite sum, they calculate infinitely, there is a crossover at some point. Or perhaps that is Borel's theorem, implies that every power series is the Taylor series in some smooth function, of some smooth function. There is a wave where at some point they converge equally. In mathematics, the Taylor series or Taylor expansion is a function of an infinite sum of terms that are expressed in terms of a function's derivatives at a single point. So it's defining that line as the single point being the connecting moment. For most common functions, the function and the sum of its Taylor series are equal near this point. Taylor series are named after Brooke Taylor, who introduced them in 1715. A Taylor series is also called Maclaurin series, where when 0 is the point where the derivatives are considered, after Colin Maclaurin, who made extensive use of this special case of Taylor series in the 18th century. Taylor series, named after Brooke Taylor, who introduced them in 1715. A Taylor series is called a Maclaurin series when 0 is the point where the derivatives are considered. So when they meet up at exactly 0. After Colin Maclaurin, who made extensive use of this special case of Taylor series in the 18th century. Okay, so every number will have every one of these infinite sums will have a certain point where they are in parallel with each other, or parallel's not the right word, where they intersect. And intersect while also running their course through each other. Where they meet and are the same. A Maclaurin series is when the only congruency is found at 0. The partial sum formed by the first n plus 1 terms of a Taylor series is a polynomial of degree n that is called the nth Taylor polynomial of the function. The nth Taylor polynomial of the function. Taylor polynomials are approximations of a function, which become generally more accurate as n increases. Taylor's theorem gives quantitative estimates on the error introduced by the use of such approximations. If the Taylor series of a function is convergent, which should mean that it's crossing. In mathematics, a series is the sum of the terms of the infinite sequence of numbers. Well, okay, that's not telling me convergent. Is convergent, its sum is the limit of the infinite sequence. If the Taylor series of a function is convergent, its sum is the limit of the infinite sequence of the Taylor polynomials. Is the sum of the its sum is the limit of the infinite sequence of the Taylor polynomials. A function may differ from the sum of its Taylor series, even if its Taylor series are convergent. Okay, so like a line can go on indefinitely, constantly building, and this one constantly building, but they would never cross each other because their distance isn't changing. But if there is some point where this one's building a little bit faster, this one's a little bit slower, where they cross, that point would be its convergent. And they would consider it the limit of the infinite sequence, because at that moment they touch, and we would count the connection of the polynomial. So if you're dealing with a shape, it's literally the empty space in between, or it's basically drawing out the empty space of our lines and saying our line connected here, our line connected here. Not specifically Taylor expansion, but a convergent in infinite space. Its sum is the limit of the infinite sequence of the Taylor polynomials. A function may differ from the sum of its Taylor series, even if its Taylor series is convergent. A function is analytic at its point x if it is equal to the sum of its Taylor series in some open interval or open disk in the complex plane containing x. This implies that the function is an analytic of every point of the interval or disk. If every line paints on this line and this line, on this line and this line, always has an inverse exact, does that mean that the video games are displaying 1, 2, and 3? Or 1, 2? Are they cutting off the mirror? Or would it be 1, 2, 3? Interesting question. Imagine that they must be kind of hiding these opposites. Not necessarily, though. Maybe if you can set something into the actual 0 point, it'll mirror. Oh. I wonder if that's how a mirror works in the video game. If they just set a specific point, give it a vertical flip, where instead of doing these two, it does these two. Where if everything is accustomed to these, or if it's these two, it's I guess it could just flip these two. Anyway, I needed to give my brain a moment to just process. Okay. So Taylor things are the Taylor series is where it is. Those convergence of an infinite series. Where n represents the coefficient, so the a of the nth term, and c is a constant called the center of the series. Power series are useful in mathematical analysis, where they arise as a Taylor series of infinitely differentiable functions. In fact, Borel's theorem implies that every power series is the Taylor series of some smooth function. In many situations, the center C is equal to 0. For instance, for Maclaurin series, in such cases, the power series takes the simpler form a n x n equals a0. So n becomes 0. X minus constant, and keeps going, equals intersect at 0, 1, x minus constant plus a 2x minus constant squared. These, okay, so you got 0 point, 1 point, and 2 point. These keep going indefinitely until they intersect. Not necessarily each other, though. Keep going. Those are fancy. Okay, a ring is an algebraic expression consisting of two binary operations, that its addition and multiplication, they always result in a positive numbers. That's why it's addition or multiplication. They obey the same basic laws as addition and multiplication of integers, except that multiplication in a ring does not need to be commutative. Oh. Multiplication in a ring does not need to be commutative, meaning that it is the same both ways. A ring doesn't need that. Ring elements may be numbers such as integers or complex numbers, but they may also be non-numerical objects such as polynomials, square matrices, functions, and power series. Okay, so a ring is a series of addition or multiplication things, and it can include expressions. In mathematics, especially in the field of algebra, polynomial ring or polynomial algebra is a ring formed from the sets of polynomials in one or more indeterminates, traditionally called variables, with coefficients in another ring, often a field. Field is a set. Field is a set on which addition, subtraction, multiplication, and division are defined and behave in corresponding operations on rationals and real numbers. A field is thus a fundamental algebraic structure in which is widely used in algebra. Okay, so it's just dealing with the area in play. Okay. In mathematics, a polynomial is a mathematical expression consisting of indeterminates, also called variables, and coefficients, which are the first part, the function, the 3x, it's the 3, that involve only the operations of addition, subtraction, multiplication, and exponentiation to non-negative integer powers, and has a finite number of terms. For example, of a polynomial of a single indeterminate, x is x squared minus 4x plus 7. An example with 3 indeterminates is x cubed plus 2xyz squared minus yx plus 1. So it's always a positive. A polynomial is a mathematical expression that uses variables and coefficients and is specifically dealing with positive values. Polynomial appear in many areas of mathematics and science. For example, they're used to form polynomial equations, which encode a wide range of problems from elementary word problems to complicated specific problems. They're used to define polynomial functions, which appear in settings ranging from chemistry and physics to economics and social science. They are used in calculus and numerical analysis to approximate other functions. Okay, it makes sense, because you're saying I'm going to deal with, say, this chemistry problem, and I'm going to be looking at how many parts I have, and at no point can I say that I have negative of an ingredient. You either have the ingredient or you don't. The lowest you can go is 0. A polynomial is always dealing with the I have it or I don't. Smallest it can go is a 0. Okay. Real numbers is a number that can be used to measure a continuous one-dimensional quantity, such as duration or temperature. So this is a have it or I don't. Real number is a number one-dimensional quantity for duration and temperature. Here, continuous means pairs of values that have arbitrary small differences. For every real number can be almost uniquely represented by an infinite decimal expansion. The real numbers are fundamental in calculus and in many other branches of mathematics, in particular their role in classical definitions of numbers, continuity, and derivatives. The set of real numbers, sometimes called the reals, is traditionally denoted by a bold R, often using blackboard bold R. The adjective adjective, real, used in the 17th century. Reen Descartes distinguishes real numbers from imaginary numbers, such as the square roots of -1. The real numbers include the rational numbers, such as the integer square root of -1. What times itself equals that? -1 times -1 would be 1. But square root negative. You can't have a square root of -1 because negative makes a positive and positive makes a positive. You'd have to have a positive and a negative, and that's not a square root. Okay, so that number isn't real. The square root of isn't real, of -1 isn't real, because it doesn't exist. It's an imaginary number. Interesting. The real numbers include rational numbers such as integer -5 and the fraction 4/3. The rest of the real numbers are called irrational numbers. Some irrational numbers, as well as all rationals, are the root of a polynomial with the integer coefficient, such as the square root of 2 and 1.414 ... These are called algebraic numbers. There are also real numbers which are not, such as pi. That's fair. And these are called transcendental numbers. Is a real or complex number that is not algebraic, that is not the root of a non-zero polynomial with integer coefficients. The best known transcendental numbers are pi and e. The number e is a mathematical constant approximately equal to 2.71828. That is the base of the natural logarithm and exponential function. That is the base of the natural logarithm and exponential function. It is sometimes called Euler's number. It's after the Swiss mathematician Leonhard Euler, though this can invite confusion with Euler numbers or with Euler's constant, a different constant typically denoted with this weird looking Y thing called Euler's constant. Alternatively, E can be called Napier's constant after John Napier. The Swiss mathematician Jacob Bernoulli discovered the constant while studying compound interest. The number E is of great importance in mathematics, alongside 0, 1, pi, and I. We'll have to get to that in a second. All five appear in one formula formulation of Euler's identity, E I pi plus 1 equals 0. Okay, we're going to learn what I is. The imaginary unit, or unit imaginary number, is the mathematical constant that is a solution to the quadratic equation x to the power of 2 plus 1 equals 0. Oh. Plus 1 equals 0. Because x squared would be any number if it's positive. Say, let's just say it's 1, for example. 1 times 1 plus 1 equals 2. If it's negative, negative, negative is plus 1 and equals 2. If we're dealing with 2, negative, negative makes 4 plus 1 is 5. And if it's positive, it's 4 and 5. Okay. An imaginary number would be where that's positive and negative. Plus 1 equals 0. Although there are no real numbers with this property, I can be used to extend the real numbers to what are called complex numbers using addition and subtraction. A simple example of the use of I in a complex number is 2 plus 3i. Imaginary numbers are an important mathematical concept. They extend the real number system R to the complex number system C, in which at least one root of every non-constant polynomial exists. See algebraic closure for fundamental theorem of algebra. Here the term imaginary is used because there is no real number having a negative square. There are two complex square roots of -1 and I and -I, just as there are two complex square roots of every real number other than 0, which has one double square root. In contexts in which use of the letter I is ambiguous or problematic, the letter J is sometimes used instead. For example, in electrical engineering and control systems engineering, the imaginary unit is normally denoted by J instead of I because I is commonly used to denote electrical current. Good to know. Okay. So, the number of e is in great importance in mathematics alongside 0, 1, pi, and I. All 5 appear in one formulation of Euler's identity, E imaginary pi plus 1 equals 0. Okay. It is E to say any number and play important and recurring roles across mathematics. Like the constant pi, E is irrational. meaning that it cannot be represented as a ratio of integers, and moreover, it is transcendental, meaning that it is not a root of any non-zero polynomial with rational coefficients. To 30 decimal places, the value of E is 2.718 2.71828 59045 23536 02874711352. The number E is the limit. In mathematics, the limit of a sequence is the value that the terms of a sequence tend to, and is often denoted using the lim symbol. If such a limit exists and is finite, the sequence is called convergent. A sequence that does not converge is said to be divergent. 10-2 uses the lim symbol, e.g. lim n goes to infinity. If such a limit exists and is finite, the limit sequence is called convergent. A sequence that does not converge is said to be divergent. The limit of a sequence is said to be the fundamental notion on which the whole of mathematics analysis ultimately rests. Limits can be defined in any metric or topological space, but are usually first encountered in the real numbers. As the positive integer n becomes larger and larger, the value of n times sin 1 over n becomes arbitrarily close to 1. We say that the limit of the sequence n times sin 1 divided by n equals 1. Oh, but technically, it never reaches. It never reaches 1. And that is why it is a sin line, because it never actually made it to 1. Okay. An expression that arises from compound interest is the sum of the infinite series. I was thinking that this was an E, but that isn't it. What is the symbol that looks like a sideways M? The symbol that looks like a sideways M is a capital Greek. Oh, the capital letter sigma, denoted as sigma It is primarily used in mathematics to represent summation, indicating the sum of a sequence of numbers. For example, summation n, or imaginary number 1, n over 1 equals 1 is a1. A imaginary is any, the a would be a coefficient or function of an imaginary number. It means the sum of the terms a1 through an. The sum of the terms of a1 through an. Oh. This symbol is a capital letter from the Greek alphabet and is distinct from the lowercase sigma. Looks like an O with a hat, which has different uses often in statistics. They are Greek letters. The first two mentioned are pi and phi, respectively. Note the spelling. What you refer to as weird E, sometimes M, is the capital letter sigma, and the one that looks like a triangle is delta. Here's the table of Greek letters and their approximate equivalents. Alpha, beta, gamma. Oh, that thing's called gamma, huh? Gamma, delta, epsilon, zeta, eta or eta, theta, iota, kappa, lambda, mu, nu. I wonder if it's chi or she or c. Omicron, pi. Looks like a B. Rho. I wonder if that's faux. Sigma, tau, epsilon, phi, or phi, chi, psi, omega. Okay, so it's a summation, and it is we just learned this, come on. Omega? No, it's before we read it. It's sigma, right? Sigma. It's summation. F. Okay. And this E is not this E. first references to the constant were published in 1618 in the table of the appendix on work on logarithms by John Napier. However, this did not contain the constant itself, but simply a list of logarithms to the base e. It is assumed that the table was written by William Oughtred in 1661. Christian Huygens studied how to compute logarithms by geometrical methods and calculated a quantity that, in retrospect, is the base negative 10 logarithm of e, but he did not recognize e itself as a quantity of interest. The constant itself was introduced by Jacob Bernoulli in 1683 for solving the problem of continuous compounding interest. In his solution, the constant e occurs as the limit. Oh. So basically, they were dealing with money, and if they made a payment that was a set amount, the amount that the compound interest was building would never, the rate at which it was growing bigger, if they made a certain payment that was like catching up to it, they were never able to make an exact payment amount that would pay it off. The last payment would always have to be a little bit extra, which is why, if you're ever dealing with payments, having your payment a tiny bit bigger makes you pay it off so much faster, because you're not underneath the line, you're cutting through the line, and it pays it off way sooner, instead of essentially holding it indefinitely until they decide the cutoff point because it's close enough. Though there would be a point somewhere along the line, 30 decimal places, or maybe even 30 years, where they would determine it's close enough. Okay. What was before this? The best known transcendental numbers are pi and e. The quality of a number being transcendental is called transcendence. Is a real or complex number that is not algebraic, that is not the root of a non-zero polynomial or with an integer or equivalent rational coefficient. So they're considered a number, which is interesting. I think the most interesting thing about it is that they're numbers that are indefinite. interesting thing that we've been able to identify pi and e as numbers. Instead of functions. Though only a few classes of transcendental numbers are known, partially because it would be extremely difficult to show that a given number is transcendental, transcendental numbers are not rare. Indeed, almost all real and complex numbers are transcendental, since algebraic numbers form a countable set, while the set of real numbers and the set of complex numbers are both uncountable sets, and therefore larger than any countable set. All transcendental numbers, also known as real transcendental numbers, are transcendental irrational numbers and irrational numbers, since all rational numbers are algebraic. The converse is not true. Not all irrational numbers are transcendental, hence the set of real numbers consists of non-overlapping sets of rational, algebraic, irrational, and transcendental real numbers. For example, the square root of 2 is an irrational number, but it is not a transcendental number, as it is a root of the polynomial equation x squared minus 2 equals 0. The golden ratio denoted what is this one again? Phi. In mathematics, the Greek letter phi is used to represent several distinct concepts. The most prominent is the golden ratio, an irrational number approximately equal to 1.61803398887, often denoted by the symbol phi. This ratio is defined by the property that the ratio of the sum of two quantities, this ratio is defined by the property that the ratio of the sum of two quantities to the larger quantity is equal to the ratio of the larger quantity to the smaller one. Oh, so the A plus B or B plus A. Mathematically expressed as A plus B divided by A equals A divided by B. A divided by A plus B divided by A is equal to A divided by B. Really? Well, if A is on both sides, let's say 3 plus 4, 7 divided by 3, it's going to be the same as 3 divided by 4. Divided by 3. If we've got 3 plus 4 divided by 3, is going to be the same as 3 divided by 4. Am I not doing something right there? Three plus 4 divided by 3. That would be 7 divided by 3 equals the same as 3 divided by 4. Those are very different, so either I'm doing something wrong or I'm probably doing something wrong. The golden ratio is closely related to Fibonacci sequence, where the ratio is consecutive terms approaches phi as sequence progresses. Another significant use of phi is Euler's totient function, which counts the number of positive integers less than or equal to a given number n that are relatively prime to n. This function is fundamental in number theory and is used in the definition of the RSA encryption system. The totient function is denoted is phi n. Additionally, phi is used in various other mathematical contexts. In spherical coordinates, phi often represents the polar angle measured by the positive z-axis. In probability theory, phi x t denotes the characteristic functions of a random variable x. The lowercase phi is also used to represent the cumulative distribution function of the standard normal distribution of statistics. I don't like phi because its math thing didn't work. So I don't get it. The golden ratio is another rational number that is not transcendental, as it is the root of the polynomial equation x squared minus x minus 1 equals 0. Oh, maybe they had it backward because or I understood it backward, but we've got x squared 3 times 3 that's not right. Except technically it is right, isn't it? Because that's 2 x's. Aren't they multiplied by each other if they're powers? Minus 3 minus 1 should be 0. But if it's 3 yeah. That's typing it in. Or is it saying that phi is the perfect number in order for it to work? The number that works is phi. That's what it's saying. The number at which it calculates true. Which is some ridiculous number. Okay. Real numbers. What's that? Rational numbers. The rational numbers, Q, are included in the real numbers, R, which are included in the complex numbers, C. Complex numbers is an element of a number system that extends the real numbers of a specific element denoted I, called the imaginary unit, and satisfying the equation. So complex numbers are every kind of number, including imaginary numbers. While rationals include the integer z. Integer is a number 0 and a positive natural number, or a negative, or the negation of a positive natural number, negatives. A set of natural numbers n is a subset of z. A set of which in turn is a subset of all rational numbers q. Itself is a subset of real numbers, like the set of natural numbers, and a set of integers. Z is countably infinite. Which in turn include the natural numbers. And natural numbers are 0, 1, 2, 3, and so on. Possibly including 0, some count starting with 0, defining a natural numbers as non-negative numbers. Some authors, sometimes the whole numbers are the natural numbers as well as 0. In other cases, the whole numbers are referred to as integers, including negative numbers. The counting numbers are another term for the natural numbers, particularly in primary education. So it doesn't include decimals or negatives. The Ishango bone on exhibition at the Royal Belgian Institute of Natural Sciences is believed to have been used 20,000 years ago for natural number arithmetic. Oh, because it's got the scratches in it. They were counting. An early case of counting. 3, 4, 1, 2, 3, 4, 5, 6, 1, 2, 3. Okay. Rational numbers is a number that can be expressed as the quotient or fraction of two integers, a numerator, and a non-zero denominator. Okay, cardinality is an intrinsic property of sets, meaning the number of two individual objects they contain may be infinite. The cardinal number corresponding to a set A is written as A between two vertical bars for finite sets. Cardinality coincides with natural numbers found by counting its elements beginning in the late 19th century. Natural numbers, okay. Beginning in the 19th century, this concept of cardinality was generalized to infinite sets. In mathematics, the singleton, also known as a unit set or one-point set, is a set with exactly one element. For example, the set 0 is a singleton whose single element is 0. In mathematics, for a function f x to y, the image of input value x is a single output value produced by f when passed x. The pre-image of an output value y is then set of an input that produces y. For the function of the map, everything on this side is the image, everything on this side is the pre-image. So, for apples, pre-image is Miriam and Gabriella, and Nala's image is pasta. In mathematics, a codomain, counter domain, or set of destinations is a function, or set of destination of a function is a set into which all of the output of the function is constrained to fall. It is the set y in the notation fx of y. The term range is sometimes ambiguously used to refer to either the codomain or the image of the function. Codomain is the image, the stuff on the right. Bijection. In mathematics, bijective function or one-to-one correspondence to a function between two sets such that each element of the second set, the codomain, is the image of exactly one element of the first set, the domain. Equivalently, the bijection is a relation between two sets such as the element is either set. Equivalently, a bijection is a relation between two sets such that each element of either set is paired with exactly one element of the other set. So bijection has one-to-one pairs. In mathematics, an involution function or inverse function is a function f that is its own inverse. So the function for all x in the domain of f, equivalently applying f twice, produces the original value. Any involution is a bijection. In mathematics, a multiplicative, inverse, or reciprocal for a number x denoted by 1x or x to the negative 1 is a number which, when multiplied by x, yields the multiplicative identity. In mathematics, an identity element or natural element of a binary operation, an element that leaves unchanged every element when the operation is applied. For example, 0 is an identity element of the addition of real numbers. This concept is used in algebraic structures such as groups and rings. The multiplicative inverse of a fraction, a divided by b, is b divided by a. The inverse for multiplicative inverse of a real number, divide 1 by the number. For example, the reciprocal of 5 is 1/5, 1/5 or 0.2, and the reciprocal of 0.25 is 1 divided by 0.25 or 4. The reciprocal function f of x that maps x to 1x is one of the simplest examples of a function which is its own inverse, an involution. Multiplying by a number is the same as dividing by its reciprocal and vice versa. For example, multiplication by 4 divided by 5, or 0.8, will give the same result as division by 5 divided by 4, or 1.25. Therefore, multiplication by a number followed by multiplication by its reciprocal yields the original number, since the product of the number and its reciprocal is 1. Inverse, the reciprocal of a designated quantity. In mathematics, one of a pair of elements in a set whose result under the operation of the set is the identity element, especially. In physics, the Lorentz transformation are a 6-parameter family of linear transformations from coordinate frame in spacetime to another frame that moves at a constant velocity relative to the former. The respective inverse transformation is then parameterized by the negative of this velocity. The transformations are named after Dutch physicist Hendrik Lorentz. The most common form of transformation parameterized by the real constant v representing a velocity confined to the x direction as expressed. What is the Greek letter y? In math. Greek letters we want. That's not helpful. Greek math symbols. Gamma. What does gamma? In mathematics, the symbol gamma, lowercase gamma, most commonly represents the Euler-Mascheroni constant, a fundamental mathematical constant approximately equal to 0.5772. This constant appears in various areas of analysis and number theory, particularly in the study of the harmonic series of the gamma function. It is defined as the limiting difference between the harmonic series and the natural logarithm. So the mathematical difference between a curve and a whole number. The Euler-Mascheroni
Mascarpone.
That's not the same word. Mascheroni. The Euler-Mascheroni constant is significant in the asymptotic expansion of the gamma function, where it appears in Stirling's approximation of large values of $and $. Another letter I don't know. But good enough. Gamma equals limit n to infinity is delta, not delta, sigma, which is the sigma is our answer. It's like our equation equals nk equals 1. Is sigma equivalent? The uppercase sigma is primarily used as a summation operator, meaning it signifies the addition of a sequence of numbers. What is the difference between sigma and equals? In statistics, the Greek letter sigma represents the standard deviation from the population, which is a measure of the dispersion or spread of data points from the population mean. It is used to describe the variability within an entire population, which is assumed to be infinite in idealized normal distribution. The symbol S is used to represent the sample size deviation which is calculated from a finite number of measurements and serves as an estimate of the population standard deviation. The key difference lies in the source of the data. Sigma is reserved for the population standard deviation derived from all possible measurements in a population, while S is used for the sample standard deviation derived from the subset of the population. The formula for the population standard deviation, sigma, divides the sum of the squared deviations by the total number of observations, n, whereas the formula for the sample standard deviation, S, divides by n minus 1, where n is the sample size, to provide an unbiased estimate of the population variance. This distinction is crucial for accurate statistical interference and reporting. Okay, so sigma is based on our numbers, this, whereas equals is definitive. And when you're dealing with polling, as in polling, taking a poll of information, you have to estimate. In physics, the Lorentz transformations are a 6-parameter family of linear transformations from a coordinate frame in space-time to another frame that moves at a constant velocity relative to the former. The respective inverse transformation is then parameterized by the negative of this velocity. The transformations are named after Dutch physicist Hendrik Lorentz. The most common form, honestly, that's a good-looking guy. He looks so happy too. The most common form of transformation, parameterized by the real constant v, representing a velocity confined to the x direction, is expressed as, oh, it's not phi, it's is it phi? I know that we just barely went on this tangent, but I have the Greek math symbols. Delta. No, gamma. I mean, that one's delta. And what is lambda again? Lambda math meaning. I remember running into it a while back. Lambda math refers to the use of the Greek letter lambda within mathematical context, particularly in the formal system known as lambda calculus. Lambda calculus is a formal system in mathematical logic and computer science for the expression computation based on function abstraction and the application using variable binding and substitution. It was introduced by mathematical Alonzo Church in 1930s as part of the research into the formations of mathematics. The lambda symbol, which looks like an upside down Y, is used in lambda expressions and lambda terms to denote the binding of a variable in a function. In this system, the lambda abstraction, written as lambda xm, defines the function that takes an input variable x and returns the body m. This notation allows for the definition of anonymous functions, meaning functions that are not given a name. For example, a function that squares its input can be written as lambda x dot x to the second power. The process of applying a function to an argument such as lambda x dot x to the second power times 7 results in the evaluation of the function with the given input, which in this case yields 49. Is it 7 times 7 then? Lambda calculus is Turing complete, meaning it is a universal model of computational compatible by simulating any Turing machine. It serves as the theoretical foundation for functional programming languages, where functions are treated as first-class citizens, and anonymous functions, lambdas, are a core feature. The system relies on two primary reduction operations. That looks like a sideways omega conversion. Alpha. Oh. Okay. Alpha conversion, renaming bound variables to avoid name clashes, and is that beta? Okay. And beta reduction, substituting the argument into the function body. The syntax for lambda calculates is defined by rules for constructing valid expressions, including variables, lambda abstractions, and applications. While the term lambda math is not a standard phrase, it generally refers to the mathematical concepts and formalisms associated with lambda calculus and its applications in logic, computer science, and functional programming. Okay. Gamma. Where T, X, Y, Z, and everything to, I guess, the power of 1. It looks like apostrophes are the coordinates of an event in 2 frames with the spatial origins coinciding at t equals t1 equals 0, where the primed frame is seen to be unprimed frame as moving with speed v. Okay, we have to back up because that doesn't make sense. The most common form of the transformation parameterized by the real constant v, representing a velocity confined to the x direction, is expressed. Okay, so something that is moving along the x-axis is expressed with these things, where I guess time x, y, and z, and time x, y, and z was then our first count, are the coordinates of an event in 2 frames with the spatial origins coinciding at time and time 1 equals 0, where the primed frame is seen from the unprimed frame as moving with speed v, so speed, velocity along the x-axis, where c is the constant, is the speed of light, and gamma 1 divided by square root of 1 minus velocity squared divided by speed of light squared is the Lorentz factor. When speed velocity is much smaller than the speed of light, the speed of light, then Lorentz factor is negligibly different from 1, but as velocity approaches the speed of the speed of light, gamma grows without bound. The value of velocity must be smaller than the speed of light for the transformation to make sense. Expressing the speed as a fraction of the speed of light, beta equals velocity divided by the speed of light. An equivalent form of the transformation is the speed of light time 1 equals gamma, the speed of light time minus beta x. X1 equals gamma x minus beta speed of light time y1 equals y, z1 equals z. Frames of reference can be divided into two groups: inertial relative motion with constant velocity, inertial, which is relative motion with constant velocity, and non-inertial, accelerating, moving in curved paths, rational motion with constant angular velocity. The term Lorentz transformation only refers to transformations between inertial frames, usually in the context of spatial relativity. In each reference frame, an observer can use a local coordinate system, usually Cartesian coordinates, in this context to measure lengths, and a clock to measure time intervals. An event is something that happens at a point in space at an instant of time, or more formally, a point in space-time. The transformations connect the space and time coordinates of an event as measured by an observer in each frame. They supersede the Galilean transformation of Newtonian physics, which assumes an absolute space and time. See Galilean relativity. Galilean transformation Galilean invariance or Galilean relativity states that the laws of motion are the same in all inertial frames of reference. Galilei first described his principle in 1632 in his dialogue concerning the two chief world systems, using the example of a ship traveling at constant velocity without rocking on a smooth sea. Any observer below the deck would not be able to tell whether the ship was moving or stationary. Dialogue concerning two chief world systems. Dialogue concerning the two chief world systems. Sopra I du massimi sistemi del mondo is a 1632 book by Galileo Galilei comparing Nicolaus Copernicus's heliocentric system model with Ptolemy's geocentric model. Written in Italian, it was translated into Latin as Systema Cosmic System, in 1635 by Matthias Berninger. The book was dedicated to Galileo's patron Ferdinando II de Medici, Grand Duke of Tuscany, who received the first printed copy in February 22nd, 1632. It consists of 4 Socratic dialogues between Copernican, Salviati, the educated layman Segredo, and centrist Simplicio. They discuss the findings of their mutual friend, the academician Galileo. Oh my gosh, that was so difficult to read. Wow. In the heliocentric system, the Earth and other planets orbit the Sun, while the Ptolemaic system, everything in the universe circles around the Earth. The dialogue was published in Florence under the formal license from the Inquisition. In 1633, Galileo was found to be vehemently suspect of heresy based on the book, which was then placed on the index of forbidden books, from which it was not removed until 1835. Whoa. 202 years after the theories it discussed had been permitted in printing in 1822. In an action that was announced at the time, the publication of anything else he had written or ever might write was also banned in Catholic countries. Overview. While writing the book, Galileo referred to it as his dialogue on the tides, and when the manuscript went to the Inquisition for approval, the title was a dialogue on the ebb and flow of the sea. He was ordered to remove all mentions of tides from the title and to change the preface because not granting approval to such a title would look like an approval of his theory of the tides, using the motion of the earth as proof. As a result, the formal title on the title page is Dialogue, which is followed by Galileo's name, Academic Posts, and followed by a long subtitle. The name by which the work is now known was extracted by the printer from the description on the title page when permission was given to reprint it with the name by which the work is now known was extracted by the printer from the description on the title page when permission was given to reprint it with an approved preface by the Catholic theologian in 1744. This must be kept in mind when discussing Galileo's motives for writing the book. Although the book is presented formally as a consideration of both systems as is needed to be in order to be published at all, there is no question that the Copernican side gets the better of the argument. Structure. The book is presented as a series of discussions over a span of 4 days among 2 philosophers and a layman. Salviati argues for the Copernican position and presents some of Galileo's views, directly calling him the academician in honor of Galileo's membership in the Accademia di Lincei. He is named after Galileo's friend Filippo Salviati, 1582-1614. Sagredo is an intelligent layman who is initially neutral. He is named after Galileo's friend Giovanni Francesco Sagredo, 1571-1620. Simplicio, a dedicated follower of Ptolemy and Aristotle, presents the traditional views and the arguments against Copernican position. He is supposedly named after Simplicius of Silcia, a 6th century commentator on Aristotle, but it was suspected the name was a double entendre, as the Italian for simple, as in simple-minded, is simplice. Simplicio is modeled on 2 contemporary conservative philosophers, Lodovico del Colombe, 1565-1616, Galileo's opponent, and Cesare Cremonini, 1550-1631, a Paduan colleague who had refused. Oh, I bet Padawan comes from that. Colleague who had refused to look through the telescope, or it's even older. Colombe was the leader of a group of Florentine opponents of Galileo's, which some of the latter friends referred to as the Pigeon League. Content. Content. The discussion is not narrowly limited to astronomical topics, but ranges over much of the contemporary science. Some of this is to show that Galileo was considered good science, such as the discussion of William Gilbert's work on magnetism. Other parts are limited to the debate answering erroneous arguments against Earth's motion. A classical argument against Earth's motion is the lack of speed sensation of the Earth's surface, though it moves by the Earth's rotation at about 1,700 kilometers per hour at the equator. In this category, there is thought. Oh, actually, it would make a difference at the equator because it would move fastest at there because it's technically a little bit more bulbous. And a little bit wider at the equator. So it would be a little bit faster there. In this category, there is a thought experiment. Oh, I hadn't really thought about it, but I wonder how fast it spins at the poles. Slow by comparison. There's a thought experiment in which... Oh, and that's why we would have all the ice form up there, because it's moving slow enough to freeze. Interesting. So it's actually partially the speed that allows it to freeze, because not, which is, I mean, because it's still salt water, but it's slow enough to freeze. In this category, there is a thought experiment in which a man is below decks on a ship and cannot tell whether the ship is docked or is moving slowly through the water. He observes water dripping from a bottle, fish swimming in a tank, butterflies flying, and so on, and their behavior is the same whether the ship is moving or not. This is a classical exposition of the inertial frame of reference and refutes the objection that if we are moving hundreds of kilometers an hour as the Earth rotated, anything that one drop would rapidly fall behind and drift to the west. Because the ship is able to maintain essentially its own, as he called it, inertial frame of reference. The ship has its own inertial frame of reference. Everything on the ship is using that inertial frame of reference. The bulk of Galileo's arguments may be divided into three classes: rebuttals to the objections raised by traditional philosophers, for example, the thought experiment on the ship; observations that are incompatible with the Ptolemaic model, the phases of Venus, for instance, which simply could not happen, or the apparent motions of sunspots, which could only be explained in the Ptolemaic and Tychonic systems as resulting from an plausibly complicated precession of the sun's axis of rotation. Arguments showing that the elegant unified theory of the heavens that the philosophers held, which was believed to prove that the earth was stationary, was incorrect. For instance, the mountains of the moon, the moons of Jupiter, and the very existence of sunspots, none of which was part of old astronomy. Generally, these arguments have held up well in terms of knowledge of the next 4 centuries. Just how convincing they ought to have been to an impartial reader in 1632 remains a contentious issue. Galileo attempted a fourth class of argument, direct physical argument for the Earth's motion by means of explanation of tides, as an account of the causation of tides or a proof of the Earth's motion. It is a failure. As an account of the causation of tides or a proof of the Earth's motion, it is a sorry, my mouth did something really strange both times there. As an account of the causation of tides or a proof of the Earth's motion, it is a failure. The fundamental argument is internally inconsistent and actually leads to the conclusion that tides do not exist. But Galileo was fond of the argument and devoted the 4th day of the discussion to it. The degree of its failure is, like nearly anything having to do with Galileo, a matter of controversy. On the one hand, the whole thing has recently been described in print as cockamamie. On the other hand, Einstein used a rather indifferent description. It was Galileo's longing for a mechanical proof of the motion of the Earth which misled him to formulating a wrong theory of the tides. The fascinating arguments in the last conversation would hardly have been accepted as proof by Galileo had his temperament not got the better of him. Why not? The dialogue does not treat taconic systems, which was becoming the preferred system of many astronomers at the time of publication, and which was ultimately proven incorrect. The taconic system is a motionless Earth system, but not a Ptolemaic system. It is a hybrid system of the Copernican and Copernican and Ptolemaic models. Mercury and Venus orbit the Sun, as in the Copernican system, in small tides, while the Sun in turn orbits a stationary Earth. Mars, Jupiter, and Saturn orbit the Sun in much larger circles, which means that they also orbit the Earth. Tychonian system is mathematically equivalent to the Copernican system, except that the Copernican system predicts a stellar parallax, which the Tychonian system predicts none. Stellar parallax was not measurable until the 19th century, and therefore was at the time no valid disproof of the Tychonic system on empirical grounds, nor any decisive observational evidence for the Copernican system. Galileo never took Tycho's system seriously, as can be seen in his correspondence regarding it as an inadequate and physically unsatisfactory compromise. A reason for the absence of Tycho's system, in spite of many references to Tycho and his work in the book, may be sought in Galileo's theories on of the tides, which provided the original title and organizing principle of the dialogue. While the Copernican and Tychonic systems are equivalent geometrically, they are quite different dynamically. Galileo's tidal theory entailed the actual physical movement of the Earth. That is, if true, it would have given the kind of proof that Foucault's pendulum apparently provided 2 centuries later. Without reference to Galileo's tidal theory, there would have been no difference between the Copernican and Tychonic system. The Foucault's pendulum is a simple device named after French physicist Léon Foucault, conceived as an experiment to demonstrate the Earth's rotation if a long and heavy pendulum suspended from a high roof above a center area. If a long and heavy pendulum suspended from a high roof above a circular area is monitored over an extended period of time, its plane of oscillation appears to change spontaneously as the Earth makes its 24-hourly rotation. This effect is greatest at the poles and diminishes with lower latitude until it no longer exists at Earth's equator. The pendulum was introduced in 1851 and was the first experiment to give simple, direct evidence to Earth's rotation. Foucault followed up in 1852 with a gyroscopic experiment to further demonstrate the Earth's rotation. Foucault's pendulum today are popular displays in science museums and universities. Okay, so it's extremely subtle, but it shows that it's ever so slightly off to one side. The side's right over it. Okay, so it is moving ever so slightly. It would have been provided the kind of proof that Foucault's pendulum apparently provided 2 centuries later. Without reference to Galileo's tidal theory, there would have been no difference between the Copernican and Tychonic systems. Galileo failed to discuss the possibility of non-circular orbits, although Johannes Kepler had sent him a copy of his 1609 book, Astronomia Nova, in which he proposes elliptical orbits, correctly calculating that of Mars. Prince Federico Ceci's letter to Galileo of 1612 treated the 2 laws of planetary motion presented in the book as common knowledge. Kepler's 3rd law was published in 1619, 4.5 decades after Galileo's death. Isaac Newton published the laws of motion and gravity, from which a heliocentric system with planets is approximately elliptical orbits is deducible. Preface. To the discerning reader refers to the ban on the Pythagorean option that the Earth moves, and says that the author takes the Copernican side with a pure mathematical hypothesis. He introduces the friends Sagredo and Salviati, with whom he had discussions, as well as peripatetic philosopher Simplicio. Day 1, Salviati starts with Aristotle's proof of the completeness and perfection of the world, i.e. the universe, because its 3 dimensions. Simplicio points out that the 3 was favored by the Pythagoreans, whereas Salviati cannot understand why 3 legs are better than 2 or 4. He suggests that the numbers were trifles which later spread among the vulgar, and that their definitions, such as those of straight lines and right angles, were more useful in establishing the dimensions. Simplicio's response was that Aristotle thought that in physical matters mathematical demonstrations was not always needed. Salviati attacks Aristotle's definitions of the heavens as incorruptible and unchanging, while only the lunar-bound zone shows change. He points to the changes seen in the skies, the new stars of 1572 and 1604 and sunspots seen through the new telescope. There is a discussion about Aristotle's use of the priori arguments, Silviati suggests that Aristotle used Aristotle's personal experience to choose an appropriate argument to prove, just as others do, that Aristotle would change his mind. Okay, we're not going to read more than that, because he said is, my brain doesn't care. One day we'll have to learn how to, once we've learned how to read Latin, we'll have to consider reading it, because why not? Gives it a use. Newtonian mechanics, specifically the term Galilean invariance today, usually refers to the principle applied in Newtonian mechanics, that is, Newton's laws of motion, holds in all frames relative to one another by Galilean transformation. In other words, all frames related to one another, such as a transformational, are inertial, meaning Newtonian's equation of motion is valid in these frames. In this context, it is something called Newtonian relativity. So in other words, it's moving, we've got something that's moving, say, 10 feet per second, then it gains 10 more feet per second, it's 20 feet per second, and then if it gains 10 more, it goes to 30 feet per second. It's maintaining its previous speed while it builds additional speed. So it just goes faster and faster and faster. Among these axioms of Newton's theory are: there exists an absolute space in which Newton's laws are true. An inertial frame is a reference frame in relative uniform motion to absolute space. All inertial frames are a universal time. Oh, the reason something can't reach the speed of light is because it's causing resistance that's slowing it down at all times, whereas nothing is slowing light. But that's not actually true, because we found that we can freeze light, so temperature is affecting light. And if temperature is affecting light, why is it able to fly through a vacuum? Because it's not actually cold, it's just the absence of matter causes it to freeze, because it's not heating up, but it's not actually cold. So light flies through it. Okay. They superseded the Galilean transformation of Newtonian physics, which assumes that an absolute space and time see Galilean relativity. The Galilean transformation is a good approximation only at relative speeds, much less than the speed of light. Lorentz transformation have a number of intuitive features that do not appear in Galilean transformations. For example, they reflect the fact that observers moving at different velocities may measure different distances, elapsed times, and even different orderings of events, but always such that the speed of light is the same in all inertial reference frames. The invariance of light is one of the postulates of special relativity. Historically, the transformations were the result of attempts by Lorentz and others to explain how the speed of light was observed to be independent of the reference frame, and to understand the symmetries of the laws of electromagnetism. And the transformations later became the cornerstone for special relativity. In physics, the special theory of relativity, or special relativity for short, is a scientific theory of the relationship between the space and time. In Albert Einstein's 1905 paper on the electrodynamics of moving bodies, the theory is presented as being based on just two postulates. The Lorentz transformation is a linear. Wow, I've never seen him look so young. The Lorentz transformation is a linear transformation. It may include a rotation of space. A rotation-free Lorentz transformation is called the Lorentz boost. In Minkowski space, space is the main mathematical description of space-time in the absence of gravitation. It combines inertial space and time manifolds into four-dimensional models. The mathematical, in Minkowski space, the mathematical model of space-time is in special relativity. The Lorentz transformations preserve the space-time interval between any two events. They describe only the transformations in which the space-time event at the origin is left fixed. They can be considered as the hyperbolic rotation of Minkowski space. The more general set of transformations that also include translations is known as Poincare group. The Poincare group, named after Henry Poincare, was first defined by Henry Minkowski, 1908, as the isometry group of Minkowski spacetime. It is the 10-dimensional non-Albion Lie group that is the importance of a model in our understanding of the most basic fundamentals of physics. 10-dimensional. Consists of the coordinate transformations of the Minkowski space that do not change the space-time interval for events. For example, it is the 10-dimensional non-Albion Lie group that is importance of the model of our understanding of the most basic fundamentals of physics. Non-Albion Lie group is a group that is the differential manifold, such as the group of multiplication and taking inverses are both differentiable. In mathematics, the Lie group, pronounced Lie group, is a group that is also a differentiable manifold, such that group multiplication and taking inverses are both differentiable. A manifold is a space that locally resembles the Euclidean space, whereas Euclidean space is the fundamental space of geometry intended to represent physical space. Whereas groups defined the abstract concept of binary operation, along with the additional properties it must have to be thought of as transformation in the abstract sense. For instance, multiplication and the taking of inverse to allow division, or equivalently the concept of addition and subtraction. Combining these two ideas, one obtains the continuous group, where multiplying points and their inverses is continuous. If the multiplication and the taking of inverses are smooth, differentiable as well, one obtains a Lie group. If the multiplication and taking of inverses are smooth, differentiable as well, one obtains a Lie group. Lie groups provide a natural model for the concept of continuous symmetry. A celebrated example of which is the circle group. Rotating a circle is an example of a continuous symmetry. For any rotation of the circle, there exists the same symmetry and concatenation of such rotations make them into the circle group. An archetypal example of a Lie group. Lie groups are widely used in many parts of modern mathematics and physics. Okay, they're all circles, all circles, all circles, all Lie groups. Is a 10-dimensional non-Albion Lie group. That is the importance of the model of the understanding. 10-dimensional, does that just mean that there's 10 different layers? In total, there are 10 degrees of freedom for which transformations. Let's read this first. The Poincare group consists of all coordinate transformations of Minkowski space that do not change the space-time intervals between events. For example, if everything were postponed by 2 hours, including the 2 events and the path you took to go from one to the other, then the time interval between the events recorded by a stopwatch that you carried with you would be the same. Or if everything were shifted 5 kilometers to the west or turned 60 degrees to the right, you would also see no change in the interval. It turns out that the proper length of an object is also unaffected by a shift. In total, there are 10 degrees of freedom for such transformations. They may be thought of as translation through time or space, 4 degrees, 1 per dimension. Reflection through a plane. Okay, in total, there are 10 degrees of freedom for such transformations. They may be thought of as translations through time or space. 4 degrees, 1 per dimension. Reflection through a plane. 3 degrees, the freedom of orientation from this plane, or a boost in any of the 3 spatial directions. 3 degrees, composition of transformation is the operation of the Poincare group, with rotations being produced as the composition of an even number of reflections. That was really complicated. In classical physics, the Galilean group is a comparable 10-parameter group that acts on absolute time and space. Instead of boosts, it features shear mappings to relate co-moving frames of reference. In general relativity, i.e., in other words, under the effects of gravity, Poincare symmetry applies only locally. A treatment of symmetries in general relativity is not in the scope of this article. So we've got X, Y, Z. Then we thought of the translation through, I guess, time would be your 4 degrees in one dimension. And then reflection is the opposite. And that would have 3, but it wouldn't have time in it. So it would have your X, Y, and Z in reflection. Reflection through a plane. Oh. Well, that's reflection through each plane. So X has got an opposite X, Y's got opposite Y, Z's got opposite Z. And then if you were to flip X and then you were to flip Y, you've got another space down there because you're flipping it in the new location, and its actual position has changed. So that's where you're getting boost. And that's adding 3 more degrees. And you've got 3. I would have counted it as 12, but I guess they're considering them the same mirror images of each other, and it's not counting them both. So it's counting 3, 3, 3, a mirror, and maybe the mirror is acting as the 4th, or it's just time. This is a metric of measurement, which is it's counting time as the 4th one, which is anything from this point to this point, the transition between the two. Okay. Okay. The Lorentz transformation is a non-linear transformation, and it may include a rotation of space. A rotation-free Lorentz transformation is called the Lorentz boost. Okay, so the mirror in Minkowski space, the mathematical model of space-time is special relativity. The Lorentz transformations preserve the space-time interval between 2 events. They describe only the transformations in which the space-time event at the origin is left fixed. They can be considered a hyperbolic rotation of Minkowski space. The more general set of transformations that also includes translations is known as Poincare group. That's a cool picture. Okay, scalar physics, or simply scalars, are physical quantities that can be described by a singular pure number, a scalar, typically a real number, accompanied by a unit of measurement, such as 10 centimeters or 10 centimeters. Examples of scalars are length, mass, charge, volume, and time. Scalars are represented by the magnitude of physical quantities, such as speed is to velocity. Scalars do not represent a direction. Scalars are unaffected by changes to a vector space basis, i.e. coordinate rotation, but it may be affected by translations such as relative speed. A change in a vector space basis changes the description of a vector in terms of the basis used, but does not change the vector itself. While a scalar has nothing to do with this change, a classical physics like Newtonian mechanics, rotation, and in classical physics like Newtonian mechanics, rotations and reflections preserve scalars, while in relativity, Lorentz transformations or space-time translations preserve scalars. The term scalar has origin in the multiplication of vectors by the unitless scalar, which is a uniform scaling transformation. In mathematics, a scalar multiplication is one of the basic operations defining vector space in linear algebra. In common geometrical contexts, scalar multiplication of a real Euclidean vector by a positive real number multiplies the magnitude of the vector without changing its direction. So something that is moving in physical space by a set metric is changing or is moving without deviation in direction. In math and physics, vector is a term that refers to quantities that cannot be expressed by a single number, a scalar, or elements of some vector spaces. A vector is a term that refers to quantities that cannot, all of that to understand that. Vectors is a term that refers to quantities that cannot be expressed by a single number. It is the rate, or it is the change. It is the change in location based on speed and time. Or to elements of some vector spaces. Historically, vectors were introduced in geometry and physics, typically in mechanics, for quantities that have both magnitude and a direction. Magnitude, greatness of rank or position, greatness of size or extent, greatness in significance or influence. One more time. Magnitude in math. In mathematics, magnitude refers to the size or extent of a mathematical object, serving as a measure to compare different size entities like numbers, vectors, or geometric shapes. For a real number, the magnitude is its absolute value, representing the distance from 0 on the number line. For a real number, the magnitude is its absolute value, representing the distance from 0 on the number line, regardless of the number's sign. This concept extends to vectors, where magnitude signifies the vector's length or size, calculated by the Euclidean norm, such as v, or vector, equals x squared plus y squared. For a vector v, x and y in 2 dimensions. Similarly, the magnitude of a complex number z equals a plus b imaginary number is its modulus given by z a squared plus b squared, which corresponds to its distance from the origin in the complex plane. Magnitude can also describe the size of geometric objects, such as the volume of a solid and the surface area of two-dimensional objects, and or the degree measure of an angle. The term order of magnitude is used to categorize numbers based on powers of 10, providing a way to understand large scale differences in size. Historically, vectors were introduced in geometry and physics, typically in mechanics, for quantities that have both magnitude and a direction, such as displacements, forces, and velocity. Such quantities are represented by geometric vectors in the same way as distances, masses, and time, and are represented by real numbers. So I've been thinking of vector as velocity, but a vector is distance from point A to point B. It is the line itself. A vector A pointing to point B. The term vector is also used in some contexts for tuples. In math, a tuple is a finite sequence or ordered list of numbers, or more generally, mathematical object, which are called the elements of a tuple. An n-tuple is a tuple of n elements, where n is a non-negative integer, where there is only one zero tuple, called an empty tuple. A one tuple and two tuple are common. For tuples, which the term vector is also used in some context for tuples, which are finite sequences of numbers or other objects of a fixed length. Both geometric vectors. Hi. STEM. Nice. I like your name. I'm just about finished up here. Went through a whole bunch and finally made it back to vectors. All to understand what scalar was. Or scholar. But we're finally back and just about wrapped up. Hope you're having a good time. Actually, I'm pretty content at the moment, but thanks for asking. I like your name. It's fantastic. Both geometric vectors and tuples can be added to the scalar. These vector operations. Scalar, is it just a number? Scalar is, you can open it back up a little bit. We're to identify it a little bit again. Basically, it's similar to velocity. It's measuring when you're looking at numbers, say something has a 1 and a 10, the distance between A and B. Scalar is basically it's that metric, the distance, the count between them. What this was for, Thank you. I appreciate that. I was learning. I was learning programming C++, and we were making velocity. And one of the things that we were doing in it was vector, and I decided to learn what vector was, and I ended up running into, let me open up this, let me open up that, and I ended up happening like 20 different tabs open and read them all until I ended up getting down to a single point. Not the full things on them, but just the little bits until I could understand it. Figure that's the best way to learn, is follow your curiosity. And I love that you're a tutor. That's amazing. Would you say that what I got on Scalar was accurate, if you've heard that one before? I imagine that it's a rather rare word to come across. I learned while doing all of this that there is so much. The math is, the more you know, the more complex it is. I'm going to go ahead and finish up this. Both the geometric vectors and tuples can be added and scaled, and these vector operations led to the concept of the vector space, which is a set equipped with a vector addition and a scalar multiplication that satisfy some axioms generalizing the main properties of the operations on the above sorts of vectors. Axioms. An axiom, postulate, or assumption is a statement that is taken to be true to serve as a premise or starting point for further reasoning and arguments. Or postulate or assumption is a statement that is taken to be true. Okay, so to satisfy some axioms, it is basically the answer that is, how long is this line? Okay. Generalizing the main properties of the operations on which operations on the above sorts of vectors. A vector space formed by geometric vectors called the Euclidean vector space, and a vector space formed by two tuples is called a coordinate vector space. Many vector spaces are considered in mathematics, such as extension field, polynomial rings, algebras, and function spaces. The term vector is generally not used for elements of these vector spaces and is generally reserved for geometric vectors, tuples, and elements of unspecified vector spaces. For example, when discussing general properties of vector spaces. Whew. Okay, well, it is time for me to go. Thank you so much for watching. I appreciate your time, and you have a great night. Bye.